Welcome to the world of sheet metal design. Whether you're a curious beginner or someone looking to sharpen your engineering skills, you're about to enter a fascinating field where creativity meets precision. If you've ever seen a computer case, a toolbox, or the sleek body of a car, you've already witnessed the impressive results of this engineering craft. Sheet metal design is all around us, shaping the products we use every day. Today, we'll break down the essential rules that transform a simple, flat sheet of metal into a strong, functional part. You'll see how a plain metal sheet can become something complex and useful through a series of carefully planned steps. This guide is designed especially for beginners using CAD software. Think of it as your personal roadmap, guiding you from a digital idea on your screen to a real, tangible product you can hold in your hands. Sheet metal design is all about cutting, bending, and forming thin metal sheets into useful shapes. These processes require both technical know-how and a creative approach to problem solving. It's everywhere, from tiny brackets inside your electronics to massive structural components in vehicles, appliances, and even buildings. The versatility of sheet metal makes it a cornerstone of modern manufacturing. The process is popular because it's efficient. Lightweight, strong parts can be made quickly and cost-effectively, making it ideal for mass production and custom projects alike. Modern CAD tools like SolidWorks and Fusion 360 come equipped with powerful sheet metal features, helping you design parts that aren't just visually appealing, but also practical and ready for real-world manufacturing. Without understanding the key rules, you risk creating designs that look great on screen, but simply can't be built in reality, leading to wasted time and resources. We'll cover the 10 most critical rules, from choosing the right bend radii to creating accurate flat patterns, so you can design parts that are both functional and manufacturable every single time. By the end of this guide, you'll be ready to create your own sheet metal designs, avoid common pitfalls, and communicate confidently with fabricators to bring your ideas to life. Why so many rules? Because metal is a real material with limits. You can't just draw any shape and expect it to work. Metal stretches, compresses, and can crack if mishandled. These rules ensure your CAD model becomes a reliable, manufacturable part. For example, a bend that's too tight can crack, and a hole too close to a bend will deform. Good design distributes stress, avoids weak points, and saves money by reducing waste and extra steps. Designing for manufacturability, DFM, means using standard sizes and simple features. Collaborate with your fabricator early and follow these rules for smoother, cheaper production. These guidelines make your designs practical, strong, and cost-effective. Rule 1. Always respect the minimum bend radius. Bending metal compresses the inside and stretches the outside. A sharp corner will crack. Every bend needs an inside radius, typically at least equal to the sheet thickness for common materials. For a 2 mm thick aluminum sheet, use a 2 mm inside bend radius. Cracked bends mean failed parts and wasted resources. Set the correct bend radius in your CAD model from the start for accurate flat patterns. Check your material's specs. Harder metals may need a larger radius. When in doubt, ask your fabricator or supplier for advice. Next, let's talk about the K-factor and bend allowance. When you bend metal, it stretches, so the flat pattern isn't just the sum of straight lengths. The K-factor represents where the neutral axis sits in the thickness. It's key for accurate flat patterns. Most CAD software defaults to a K-factor around 0.44, but check with your fabricator for precision. The bend allowance is the extra material needed for the bend. Your software calculates this using the K-factor. Get the K-factor wrong, and your part won't fit as intended. For simple parts, defaults work, but for tight tolerances, always confirm with your shop. Accurate K-factor input means your parts will assemble perfectly. When you bend sheet metal, the stress isn't limited to just the bend line. it actually spreads out into the surrounding material, which can lead to problems if not addressed. That's why relief cuts are so important. These small notches at the edges of bends help prevent tearing, bulging, or unwanted deformation, especially at the corners where stress is highest. A bend relief is a precisely placed cutout at the end of a bend. It should be slightly deeper than the bend radius and at least as wide as the material thickness, ensuring the metal can flex without damage. Most CAD tools can add these reliefs automatically, but it's important to know how to adjust their size and shape for your specific application. Also, avoid designing sharp internal corners. Always use fillets instead. Sharp corners act as stress concentrators and can easily crack during bending, especially in harder or thicker materials. Fillets, on the other hand, help distribute stress smoothly, making the part not only stronger, but also much easier to manufacture and finish. As a rule of thumb, the fillet radius should be at least equal to the material thickness, but going slightly larger can further reduce stress and improve durability. These small design tweaks, adding reliefs and fillets, make your parts not only stronger, but also much easier and more cost-effective to fabricate. In summary, bend reliefs and fillets are essential features for creating durable, reliable, and manufacturable sheet metal parts that stand up to real-world use. Hole placement matters. Holes too close to bends will distort. Keep holes at least 3 times the material thickness away from any bend. If a hole must be closer, drill it after bending, but this adds cost. Flange sizing is also critical. Too short, and the tooling can't grip. Too long, and you waste material. Minimum flange height should be 4 times the thickness plus the bend radius. For a 2 mm sheet with a 2 mm radius, that's at least 10 mm. Proper hole and flange design ensures accurate, easy manufacturing. Simple adjustments here save time and prevent costly errors. Always use a uniform thickness. Sheet metal starts as a single, flat piece. All operations, cutting, bending, punching, assume the same thickness throughout. If you need different thicknesses, design separate parts and assemble them. Simplify your bends. Fewer bends mean lower cost and faster production. Keep bends in the same direction and on the same line when possible for efficient setups. Use standard bend angles, 90 degree, 45 degree, 30 degree, to match common tooling. Consistent bend radii allow for single machine setups. Avoid unnecessary complexity. Simplicity leads to better, cheaper parts. Uniform thickness and simple bends are the foundation of good sheet metal design. Before sending your design to the shop, always check the flat pattern. The flat pattern is the 2D shape cut from the sheet before bending. If it's wrong, your part will be too. Use your CAD's unfold or flat pattern tool to inspect for errors or impossible features. Optimize the layout for efficient cutting and add tabs if needed. Next, apply realistic manufacturing tolerances. No process is perfect. Standard tolerances are plus 0.25 mm for dimensions and plus 1 degrees for bends. Only use tight tolerances where absolutely necessary. They increase cost. Discuss tolerances with your fabricator to match their capabilities. Careful flat pattern checks and smart tolerancing make your designs manufacturable and affordable. Let's put these rules into practice by designing a simple electronic enclosure box. This process will help you understand how to apply sheet metal design principles in a real-world scenario, step by step. Start by selecting a 1.5 mm thick aluminum sheet, which is a common choice for lightweight yet sturdy enclosures. In your CAD software, model a 100 by 150 mm rectangular base as the foundation for your box. Use the base flange tool to set the uniform thickness across the entire part, ensuring structural consistency and manufacturability. Next, add 4 50 mm high walls using the edge flange tool. Set the inside bend radius to 1.5 mm, which matches the material thickness and helps prevent cracking or deformation during bending. Adjust the K factor to 0.44 for accurate flat pattern development. This value compensates for material stretching and ensures your flat pattern will fold into the correct shape. The CAD software will automatically add bend reliefs and fillets at the corners, which are essential for smooth bends and to avoid tearing at sharp edges. Place all mounting holes at least 4.5 mm away from any bend line. This precaution helps prevent distortion or weakening of the material around the holes during the bending process. Add 10 mm wide flanges at the top of the walls to support the lid. This width is well above the minimum required, providing extra strength and easier assembly. Keep all bends at a precise 90 degrees and use consistent bend radii throughout the design. This standardization simplifies manufacturing and ensures a professional finish. Unfold the box using the flat pattern tool in your CAD software. Carefully inspect the flat pattern for any errors or overlaps that could cause issues during fabrication. Add a general tolerance note of plus 0.25 mm to your drawing. This ensures that all dimensions are achievable and that the parts will fit together as intended. By following these 10 essential rules, you'll create a strong, accurate, and manufacturable enclosure. Now, open your CAD software and try modeling this enclosure yourself to reinforce your learning.